Hello and welcome to today's webinar. I am Dennis van Helder from the Global CCS Institute. I will be the MC for today's webinar. The topic of today's webinar is CCS systems modeling and simulation. This will be presented by Alfredo Ramos from Process Systems Enterprise, who is located in the UK. I'll introduce Alfredo shortly. This webinar is part of our broader program of webinars to cover different aspects of CCS. This slide shows the planned webinars for 2013-14, and around half of these have now been completed. The webinars have been recorded and are accessible from our website. This current webinar will also be recorded and will be made available on our website in the near future. We'll welcome questions asked throughout the presentations. If you'd like to ask a question, please type this into the GoToWebinar control panel. I'll moderate these questions and post them to Alfredo at the end of his presentation. Alfredo, welcome, and please start your presentation.
Thanks, Dennis, for the kind introduction. I'm now going to show my screen. Good. Many thanks again, Dennis, and not only to you, but also for the Global CCS Institute for the opportunity to present our work within this forum. I'd like to welcome everyone to this webinar on CCS system modeling and simulation. We have a dense program ahead of us today, so I'd like to start by sharing an overview of this talk. I'd like to start with an introduction to PSE, and I promise this will be a very brief introduction, and then I will move on to provide you with some background information into the activities in CCS and Process Systems Enterprise and the role of system modeling for accelerating deployment of CCS at a commercial scale. I will then introduce the Energy Technologies Institute-funded CCS System Modeling Toolkit project, and will then move on to present the results of a case study for an integrated CCS chain. We'll look into both steady-state and dynamic analysis of the chain. Finally, I shall provide some concluding remarks. Process Systems Enterprise is a spin-off from Imperial College in London. In 1997, PSE acquired the rights for the advanced process modeling platform GPROMS and established itself as a private independent company. 16 years down the line, we have experienced substantial growth and achieved a global presence with offices in the US, London, where our headquarters are based, Germany, South Korea, and Japan. We're also represented by agents in various countries in the Middle East and Asia. Our business is split in software, roughly about 60% of our revenue, and engineering services. We have a major process industry focus, but due to the flexibility of our platform and the expertise in our engineering teams, we have quite a number of applications in sectors considered as non-traditional ground for process modeling. In the last 3 years, we have focused our efforts in 4 verticals, namely oil and gas, chemicals and petrochemicals, life sciences, consumer products, and power and CCS. We have now specialist products for these sectors, all based on our GPROMS platform. Those of you familiar with GPROMS will recognize the difference in the content provided by these products. We have now, rather than a platform that will allow you to develop any type of model, these products come with validated model libraries with components that can be used to build process model in a drag-and-drop fashion. I hope this was a brief enough overview of our activities, but still good enough to raise awareness of what we do in our work. And now, without further delay, I would like to move on and focus on system modeling for CCS. Think about CCS systems and the multiple challenges that are faced by stakeholders along the CCS chain. I think we could easily agree or recognize that these challenges have been faced by the different industries in isolation in a routine fashion. A number of tools have emerged and exist for decades that deal with the challenges in these areas and help engineers to tackle the technical issues. However, the software packages normally apply to a single area. It might apply to various, but as a common denominator, we could say that these tools are normally point solutions that do not allow a large degree of integration along the CCS chain. In fact, some of you may remember a webinar by, oops, sorry, mistake. Some of you may remember a webinar by Vladimir Weissman from Worley Parsons in this forum, also presented at the Global CCS Institute's webinar. This was, I think, back in March this year, where he reported the difficulties experienced in carrying out a thermodynamic modeling study for post-combustion carbon capture for a pulverized coal power plant. I think Vladimir reported having had to use 4 different software packages to perform this task. And actually, this is the gap that we feel that needs addressing. In fact, we're convinced that system-wide modeling will support organizations across the CCS landscape to explore the complex decision space more rapidly, helping them to resolve own technical and economic issues while taking into account upstream and downstream behavior. We need to remember that some of these projects are formed by consortia that will include different parts and different engineering departments, and yet you need to know what impact the design and operation of the units up and downstream will have on your own assets. Now, systems-wide modeling will provide a means to manage interactions between the stakeholders along the CCS chain, and it should be helpful to find the optimal trade-offs in design and operation. It is meant also to be an integrating platform for technology development, easing the way for not only collaborative R&D work, but also feed studies carried out jointly by multiple partners in a CCS project. This holistic view will certainly support decision makers to manage the complexity and risk of CCS projects at a multi-scale, network-wide level. However, we're certainly not alone with our views. In fact, a survey carried out by the Energy Technologies Institute among its members for requirements for accelerating CCS technology development identified system modeling as a key enabling technology for the commercialization of CCS. And to this effect, the ETI, for those of you who are not very familiar with the Energy Technologies Institute, it is a private-public partnership with public partners, the Department for Business and Innovation Skills of the UK and the Department of Energy and Climate Change, and 2 of the research funding organizations, the EPSRC and the Technology Strategy Board. Together with some private companies on the oil and gas side, we have Shell and BP, on the utilities, Aon and EDF, and then equipment manufacturers, vendors, Caterpillar and Rolls-Royce. The ETI sets this system modeling toolkit project, and a consortium formed by European utility companies Aon and EDF, Rolls-Royce, CO2 Deep Store, and PSE and E4Tech set about developing the software package based on our GPROMS modeling platform and our process modeling expertise. The objective of the project is to deliver an end-to-end CCS modeling tool called GCCS, which will hit the market in the 2nd quarter of 2014. The initial scope of GCCS will cover process models for power generation, both conventional and non-conventional, solvent-based CO2 capture, CO2 compression and liquefaction, CO2 transportation, and injection in subsea storage. It will also contain a pre-configured pre-configured material models, so for physical properties, that are optimally adjusted to the various subsystems in the CCS chain. You will notice that we have chosen a very innovative equation of states for the mixtures downstream the power plant. In fact, PSE acquired the rights to commercialize the SAF technology developed at Imperial College as of last year, and GCCS will incorporate the state-of-the-art equation of state from its release. Some of you might wonder why to go this length for the physical properties calculation for these mixtures, particularly for near pure CO2 streams. I think the next slide will provide a clear indication as to why it is necessary to follow down this path. And this is what we can see here, is actually the vapor pressure over temperature for pure CO2, and for a mixture, and these are the data points that are shown here and as black squares, for a mixture of CO2 and 2% of hydrogen. what we also can see is, firstly, if we analyze this, and you might remember that some studies on the feasibility of CCS were carried out with pure CO2 providing the physical properties or physical properties of CO2, viscosities and densities, etc. And you may have recognized that even for 280 Kelvin, or we can see that the difference in vapor pressure is roughly around 30 bar. So impurities are extremely relevant to the phase behavior of these near pure CO2 mixtures and need to be taken into account. Now, if we look at something that has been adjusted for similar mixtures like GERC, okay, arguably this is not for the high CO2 purity end, but more on the methane side for natural gas mixtures, but still has been extensively validated for mixtures including all those components. We'll see that it still shows a mismatch of about 5 bar in the relevant region for the vapor pressure. And this is exactly where we feel that GSAF or SAF technology that we have acquired closes the gap, as it's able to predict the impact of impurities quite accurately. Now, to just briefly go back, the final point of the tool, and this is in the spirit of allowing collaboration between the different stakeholders along the CCS chain. The tool incorporates open architectures that allow incorporation of third-party models. We have tested these. For example, in fact, GCCS will come with a standard interface to E.ON's Pro 80s, which is a steady-state simulator for power plants, and also has been tested for a set of design procedures from Rolls-Royce for compressor systems. Now, moving on to the case study, what can you do with GCCS? I'm going to present now the results of one of 4 major case studies that are designed to validate the tool. And let me start with a system overview. We have modeled an 800 megawatt supercritical pulverized coal power plant with the help of E.ON. We designed a chemical absorption plant using a standard MEA solvent designed for 90% CO2 capture, and then coupled it with 4 compression trains where we have 2 frames a train and also all necessary surge control elements. Obviously, Rolls-Royce we see a key to the development of these models. And then we coupled the whole system with 220 kilometers of pipeline, both on and offshore, and then a corresponding dense phase injection with 4 injection wells in about a reservoir that was in about 2 kilometers depth. All these systems have been put together with our consortium partners. So basically, PSC developed the component models, and then within each of the subsystems, if you are in the tool, you'll be able to drill down and build the molds of each of these plants. Now, if we were to look into the power plant in more detail, you can see, okay, this is a non-trivial model of a power plant. We have here the pulverized coal boiler, a supercritical one, then a high pressure, intermediate pressure, and low pressure, turbine sections, generator, condenser, then a series of feed water heaters, and as you can see also a number of recycles. I think, and obviously we have a closed loop, closed water steam loop in here. This is normally a rather challenging system to converge, but I can say that the way that this has been implemented and exploiting features of the GPOMS platform, we're able to converge this flow sheet from scratch by only providing initial guesses here for flow and temperatures of these streams. The key here obviously is if you're modeling real assets, you will have access to the stream data and you will be able to converge the flow sheet easily. The way that these models are used, in a first step, the user will calibrate the models to a given set of conditions. What we mean calibrating is the user will be able to specify the inlet and outlet conditions, and for example, the system will calculate the heat transfer area of a heat exchanger, or in terms of a steam turbine, the internal parameters of simple modes like the ellipse law, so Stokes constant. Once this calibration is finished, the user can use the parameters that were calculated by the GCCS model, and then predict performance of the plant at various loads. And this is in fact how we proceeded with the case study. We compared our results with those of existing models on Eon side that have been validated against plant data. On the capture side, we have a full MEA loop. This is a fully dynamic model with inertial terms on the key volumes of the system, so sumps, absorber stripper columns, and obviously a reboiler condenser and makeup tanks. We have implemented the relevant control elements that will make sure that the plant responds to disturbances. And this is something we'll see later on the dynamic study. Just to look into something, again, going back to the webinar delivered by Vladimir Weissman, one of the things that you can do with this tool is obviously look at the optimal point for the steam draw for the amine regeneration. And in this case, well, there are several potential points for draw off. I mean, some are obviously not suitable owing to the high temperature and high pressure and therefore high efficiency penalty. But for some, the pressure might be too low, and obviously there might be an optimal point to find it. You could see that basically these 2 points, so the IP to LP crossover and maybe one of the steam draw-offs of the low pressure turbine section might be suitable. However, while that might work at 100% load, if we go down to part loads, this pressure may drop below the pressure required for the amine section. Therefore, for example, in this case, we opted to have a certain reserve, and you can simulate and go down to part loads and see whether you still fulfill that pressure requirement. In this case, you can select here the optimal draw-off point. Moving on to the third subsystem along the chain, this is the CO2 compression plant. Here we see one of the trains with 2 drives. One is a fixed speed, the other is a variable speed electric drive. Arguably, for CO2 systems where you might have integrally geared compressors, you would be looking into changing the guide vanes rather than the speed, but that's something that can be easily adjusted. You can also observe that whenever we have a draw of material and a cooling section or a knockout drum, we have a compressor section, and then obviously for the purpose of control, surge control, we'll have also recycles implemented and surge valves that would open whenever the compressor section gets close to the surge limits. There's a very basic dehydration unit model here that simply computes the energy requirement for this step. Further on, we have the CO2 transmission pipelines. These are, again, fully dynamic models, including all the holdups for the system and basically dynamic mass, energy, and momentum balances. And they would describe the topography of these pipelines. Here we have the topography for the onshore pipeline. Here we have the 20 kilometers and then a change in elevation of 160 meters. Then on the other side here, the offshore pipeline, and we can see drops very quickly down to minus 200 meters to the seabed and keeps there till we reach the vertical riser up to the platform. There are also some other elements included, like CO2 flow meters, and you can include any bends, T's, and Y junctions that might be along the pipeline as point pressure drops. Finally, the CO2 injection and storage with the corresponding header, choke valves, and then wellhead connections, and finally wells down to a reservoir. Very important to say here is the effect of heat transfer on these wellhead connections. This is a bit of tubing that might be first above water and then submerged. In this case, we took the specifications for something similar to King's North, and we had 20 meters above water, 70 meters submerged. We actually saw a huge impact on the pressure drop calculations if you didn't include these connections, just simply because of the differences in heat transfer to the environment. Now, for those of you interested in the maths, might be quite few, system comprises over 29,000 equations or variables. Of those are things of roughly 2,000 are differential, And in terms of computational time, and I guess this is the most interesting for you, this has been done, it says here desktop computer. Actually, these calculations could be done on the standard laptops that we use here at PSE. Basically, a steady state calculation would require roughly 200 seconds. It will be much less for sensitivity runs. We just simply change certain input conditions. Let's say, talking here about a hot start of the model. Once you have it loaded in memory with a solution, it's very easy to move. And then for a 50-hour dynamic simulation, it takes roughly 7 hours to provide the results for the transient study. Now, let's have a look at the results. First, for a steady state analysis. In this case study, and for the system I showed earlier on, we considered 5 different scenarios. The first scenario with 3 variants aimed at describing the base load of a power plant and assessing how well GCCS is capable of modeling these. The power plant operation was then simulated at 175 and 50% without any capture involved at all. Then we moved on to set the base load of the CCS chain. That included basically 2 cases. So 100% nominal load, of nominal load, sorry, we looked at 90% and 50% capture. And then we looked into part load analysis where we captured 90% of CO2 but only at 75 and 50% load on the power plant. Finally, we also wanted to look into the impact of extreme weather, and we looked at summer and a winter case. Obviously, it is required to say that the 100% power plant operation was used for the model calibration, as we said earlier. So heat transfer areas for feed water heaters, as well as contents for steam turbines. And with respect to the temperatures considered in the system, this is the base case. So we can see that we consider different temperatures for cooling water, air, and seawater, and that we varied those to different extremes for the summer and winter scenarios. We also consider the geothermal gradient of about 27.5 degrees Celsius per kilometer for the heat transfer in the wells, or of the wells with the environment. Now, in terms of power generation, here we can see the results for the first 3 cases would be for the standalone power plant, and then we have the different cases for 90 and 50% capture at 100% load, and then for the part load scenarios, and finally for the summer and winter conditions. What we can see here is that there's a difference, obviously, between the net and gross power generated. The delta results from the coal milling and the power plant auxiliaries. On the other hand, we also have the same difference for well, let's say, if we look at the case where we're capturing the CO2, the addition here would be CO2 compression on that side. Now, the difference, obviously, between the gross here, between a case that is capturing CO2 and one that is not, is obviously the captured plant steam, or the requirement, or the steam requirement of the capture plant, and the CO2 compression. Maybe so relevant to say that you might see differences here between the gross power output of the 100% and 90% capture and the corresponding scenarios for summer and winter conditions. These are mostly due to differences in viscosities along the CCS chain. And this is something that can be seen from the compression power. Again, you see these minimal differences between the 100% and 90% capture and the corresponding summer and winter cases, where this variation can be traced back to changes in physical properties. Now, this is a very brief overview of the steady state results. Perhaps it would be worth saying that we have compared all these studies with information that is available in public literature, but also to the European Benchmarking Task Force reports on post-combustion capture, and that both the results for the power plant standalone, but also for the integration of power plant and capture were in very good agreement with what was reported by the EBTF report. Now, with respect to dynamic analysis, we wanted to test the capability of the tool to simulate rather challenging dynamic scenarios. So we have rapid changes in power output on the plant, and we also, as a secondary measure, wanted to basically check what effect these changes would have on the CCS chain according to our model predictions. For that, we designed a scenario in which we start at a constant, or let's say a maximum continuous rating for the power plant, then drop down to 75% load, stay there for 1 hour, and then ramp up again with the same gradient back to maximum continuous rating, and then we just let the system settle down back to steady state over a period of almost a day. These ramps here that we imposed on the load were actually also imposed on the boiler side, and the gradient that we selected here was something that would be in concordance with basically the recommendations for the safe operation of pulverized coal boilers. Now, what we can see, and from the simulation results, now I start here with the power plant, is that at the beginning the coal mass flow rate will follow the disturbance that we have imposed on the system, but then actually it will take about half an hour to reach the steady state value for 75%. At the time where we switch, again, it will follow relatively quickly, but again, it will take again about half an hour to settle back to the steady state once we go up to full load. If we observe the power plant net efficiency, we see that we have certain disturbances reflected, and that coincide with that 30-minute period that takes the power plant to settle back into a steady state. I think a rather interesting aspect here to mention is here the LP turbine inlet valve stem position. This LP turbine inlet valve was used to maintain the steam requirement to the reboiler, which basically said that we needed at least 3.5 bar absolute here to be delivered to the capture plant. So whenever we see that this might drop, this valve will quench the flow to the low pressure steam section. This is exactly what we see here. And again, what you can observe is that the steady state requirement sees more steam flowing into the LP turbine than it actually does during the first change. And again, it takes about roughly 30 to 40 minutes to settle to that steam value. So this actually leads us to think that more steam is actually being diverted to the capture plant in this initial 30 minutes following the disturbance. And this is actually what we can appreciate in the next set of results concerning the capture plant. And we can see here basically the steam, the capture rate actually basically moving up, retaining the plant capturing more CO2 that they actually want. We have set up control systems here that would ensure that the capture rate is meant at 90%. I think at this point it's worth mentioning that we didn't do any effort to optimize these control loops. So we made sure that they were stable and they would be able to bring the power plant and the whole system back to steady state, but these are not optimized. Now, what we can observe, and most importantly, is that the steam requirement to the reboiler here has a substantial, what would you call, a delay in following the original disturbance. And this also can be seen here on the CO2 production rate. Again, it takes about this half an hour that we saw on the power plant side to go back to the steady state. And again, when we move up to 100% load. These disturbances are also appreciated in the reboiler load, basically in the consumption in gigajoules per ton of CO2, and then further down on the solvent demand. Now, if we observe this more closely, we can see that there's a two-way coupling between the power and CO2 plant. There's nothing surprising, but I think what is relevant to see here is that this is being captured by the tool, and this is something you only capture if you run these two models jointly. You can see again here how the power plant net efficiency would drop against the reboiler steam demand, and only when you get back to the steady state we will recover again the efficiency that we would expect for the steady state at 75%. Now, what is the origin of this disturbance? If we just monitor the different sample levels of the two columns, the absorber and the stripper, we will see that the holdups are shifting substantially between these columns. And in fact, they're all accumulating down in this buffer tank storage that is just underneath the, or you can see it to the left of the stripper sump. And an interesting result was that we obviously didn't provide any control here for the level of this buffer tank. And what you can see is that its level increases. We relax the control for this one. What you can see is that the level increases to what would be in theoretical terms 200% of its actual capacity. What this means is that when we set up this study, we didn't size this buffer tank as we should have. Obviously, this doesn't impact the simulation, it just continues, but in a real system, this would have been a problem. So again, this is something that you need to take into account when you're looking into load changes. Moving on to the compression plant, you can see here the different power requirements for the two drives, and we can see that there's a propagation of disturbance in terms of the at the inlet pressure to the dehydrator. And interestingly, obviously, that disturbance is not propagated that well to the compressor discharge pressure. On the other hand, we can see that all sections, both on the fixed speed side and on the variable speed or side, would go into surge, obviously at different points. The last one to go into surge being section 3 here, connected to the second driver. And obviously all the valves in this simulation are switching to being controlled, and all the recycle loops would open so as to avoid the compressor sections going into full surge and maintaining a surge level of about 10% of the surge margin. Finally, in terms of the transmission pipelines, and please note that the timescale here have changed. Before we're looking at a timescale of 10 hours, and we're now seeing something that is around 50 hours. We can see that, interestingly, the change in mass flow rate is not as substantial as we would see on the injection side of things. So if I maximize this plot, we can see that at the pipeline inlet there is a substantial change in mass flow rate, but this is dampened down as we move over or along the pipeline and up the vertical rises. So at the end of the day, at the pipeline outlet, the change in mass flow rate that we see is about 4% of the initial mass flow rate, and this actually speaks for a substantial buffer potential on the pipeline side, even though that we're looking at a supercritical dense phase system. And this is a question that has been asked by various parties. Always is how much buffer is actually there for a dense phase or a supercritical system. So the answer is still substantial. And finally, we can see it here on the injection and storage side that again the mass flow rate change is rather minimal. So as we said, for roughly 4%. Good. Conclusions. I think we've demonstrated that we have developed a system that is basically will support the model-based engineering of CCS chain. It can be used by the diverse stakeholders along the CCS chain, and they may have different concerns and priorities. They will be able to coordinate these activities with this single tool within a single environment, owing to the or thanks to the third-party interfaces. You also could imagine that different organizations could share their models within the same platform without having to disclose their IP. This CCS system is very complex. It also demands having very detailed models that can capture the key phenomena in the system. And we also could observe that there are complex steady state and dynamic interactions along the elements of the chain, and one cannot look into these in isolation. The good thing is, on the other hand, is we've demonstrated that this is within the capability of current state-of-the-art modeling technology, and we have provided a demonstration of an end-to-end modeling tool that can basically help to capture, formalize, and deploy existing knowledge in CCS technology, can provide a common language for communication among the stakeholders or along the CCS chain, and given it, and thanks to its open architecture, allow incorporation of future technology. In terms of timelines, where are we now? Well, we have made a GCCS version 1.0 Alpha 1 for selected universities and research consortia, and some lead users among industrial partners. They have been working with it for a few months, and we're keen to have the feedback. In a 1 to 2 months timescale, we will be releasing an Alpha 2, which its main feature would be the incorporation of the physical property models for CO2 capture, compression, and transport using our own package, GSAFT. And then within a 5 to 6 months timescale, we expect the beta release of the tool that would be in Q2 2014, in which we will be incorporating costing functionality, and obviously we'll have streamlined all component models, have performance enhancements in terms of execution speed, and finally, obviously, online documentation and training. I would like to, before concluding, I would like to first acknowledge the ETI and our consortium partners. This work was carried out as part of this project, commissioned and co-funded by the Energy Technologies Institute. And foremost, I would like to thank the CCS technology team, all of them. They've been outstanding, and the development of this tool, and have provided an engineering insight into completing the different case studies for GCCS. And specifically, I would like to thank Gerardo Sanchis, Mario Calado, and Drs. Adekola Lawal, Javier Rodriguez, and Nuri Samsafli for all their efforts. With this, I'd like to thank you for your attention. I would like to hand back to Dennis for the moderation of questions.
Thank you, Alfredo. That was an excellent presentation. We provided a good overview of systems modeling and simulation, and also highlighted how to work through process systems enterprise can be used to better understand CCS systems. We've got a few questions from our audience, and I'd like to pose them to you now. The first question was when you were talking about the mixtures of CO2 and hydrogen, you showed a mixture of 98% CO2 and 2% hydrogen. Can calculations be done for other gas compositions as well, for example, including nitrogen and methane and so forth?
Yes. In fact, we include a set of components that for now we have fixed. They include all the usual compounds that are found in post-combustion and pre-combustion capture CO2 mixtures. So you will have methane, you will have nitrogen, hydrogen, water, obviously very important. SO2 will be there as well.
Okay. That's interesting. So the leading on from this question, there was another one about impurities in the gases, and linking it to the regulatory aspects. Is that at all accounted for? How do you account for the to change these impurities in terms of looking at the storage integrity, for example?
Sorry, Dennis, I'm not quite sure that I understand the question. So this is how we account for changes in composition along the chain, or?
No, how this question was more related to the regulatory frameworks regarding the geological storage integrity.
Mm-hmm. Okay,
whether
good.
there's different requirements for the regulations of what impurities you can have when you model that.
Mm-hmm. Understood. No, basically, if you think back at the whole system picture that I presented, and more specifically on the injection and storage side, you would have recognized a module that is a reservoir model. At the reservoir side, initially we wanted to have a complex approach and also, let's say, have a finite volume model of the reservoir, looking into account how the dispersion of CO2 occurred over the close vicinity of the reservoir. But very quickly we saw that, let's say, the complexity, especially on the model attribution side for the reservoir, and taking into account the different lithologies for the system and then different layers that will be there, would go beyond any system modeling tool. So what we have provided here is an interface to reservoir simulation. In fact, what we expect, and this is what we have done, is for experts in simulation of storage systems to run out certain simulations for certain boundary conditions, and the interface at the moment is a relationship between injected mass of CO2 and pressure increase in the reservoir. But this is something that we don't look into with detail.
Okay.
Yeah. Mm-hmm.
Okay. Going back to the sources of CO2, in one year's slides you showed that you're looking at post-combustion capture and oxy-fuel, I think. Mm-hmm. It looks like that's mainly based on coal-fired power generation. Do you consider other sources as well, such as from natural gas processing or, say, from oil refining or cement sector?
Mm-hmm. Yeah. I think for this, we need to differentiate between what are the outcomes of the project of this ETI-funded SMTK project and what the tool is capable of. As for the project, the moles that would be provided as standard part of the package are just for power generation, so conventional and non-conventional, IGCC, CCGT, oxy-fuel, and powderized coal. However, obviously, from our work, we're mainly a company that works with the process industry, so especially for cement and actually for steel making, for example, and also on the natural gas processing side, we have molds in-house that have been developed by our partners on the petrochemicals and chemicals and on the oil and gas side, and also with our, basically these are molds that you can take, any mold that you have on the GCOMS platform could be used in GCCS and couldn't be implemented there. So let's say the right question would be for the release is not that you will have component molds for cement and so on, but this is something that can that we have in-house and might be becoming a standard part of the tool in the second half of 2014.
Okay. Okay. There's a few questions around the whether there will be a report made publicly available on the ETI project.
Yeah, this is obviously all these case studies we need to report to the ETI back, and this is probably more a question for the ETI to reply, but I'm very much aware that given that, and this is something I haven't said, I think we've consulted quite a bit of state-of-the-art literature. This is the first ever simulation of a whole CCS chain, including all components on the capture and the source side, and up down to the injection. And obviously, the ETI is quite interested in making this a bit more official with a press release, and also at some point also sharing the reports. But that probably is a question for the key stakeholders at the ETI.
Yeah, yeah. There's a few questions as well about the licensing and the testing of the or the reviewing of the software. Yeah. There's a question of whether there's going to be licenses available for all universities in the UK, or if you've already selected your partners.
Mm-hmm. Yeah, at the moment we would like to work with everyone if it is possible. It's simply the earlier feedback we have on the tool and things that people would like to see, obviously the better, because that will give us input for our development teams. Now, we also have to be conscious of our bandwidth, and at the moment we're working with 4 universities in the UK, and it's up to 7 universities in Korea, and it's basically Korea mainly because we have a presence of have had a presence in Korea for the last 5 years, and the UK obviously because of our ties to local universities. Up to now, we have been trying to get the licenses, the test licenses out. The key problem has been around the integration with our physical properties package. We've been using something else that required additional licensing. But now with the Alpha 2 that will be coming out in early January, we'll sort this out. And basically, I would say whoever's interested in testing the tool should contact us, and we'll find a means of getting them onto the evaluation program.
Okay. And when the evaluation program is completed and the software is commercially available, do you have an indication of how much it would cost?
That's a question that we are currently answering internally. But let's say it will be in the same order of magnitude of what our current platform costs are. In terms of academic licenses, there will be something. One has to understand that basically with GCCS, you don't only have access to, if you go for a developer license, to the full GPROMS platform, that is all the content that is included. Let's say in terms of academic and industry prices, you would expect a certain premium to what is our model builder, so the basic GPROMS, but it definitely will be in the same ballpark.
Okay. Okay. There's been a few questions about regulators and policymakers. Have you had much input from them in developing the software?
Yeah, actually, this is a very good point. Let's say that the tool has been, and obviously because of the time frame of a limited time frame of this webinar I couldn't show, we've been considering all the time in the development of the tool 3 different tiers of users. There's the tier 1, which is basically someone like us, but also R&D people across companies and also universities who will develop their own models. And for example, you could easily see that, let's say, new absorption models might be something that needs to be developed, especially with all the effort that is going on in these absorption technologies. These people will develop these things, will also package these models and make them available to other parties. So that's what we call tier 1. Tier 2 would be the standard engineering user, who actually will put together process models like this case study that we presented by doing a drag and drop, checking their isometrics, looking at specification of pipelines and so on. And we'll also be able to do optimization calculations to design their systems. But finally, we have also something that is what we call a tier 3, which might be someone who's only interested in carrying out high-level studies. And that might be, let's say, you might want to look at, let's say, changes in OPEX by looking to different classes of CO2 and how you, the cost for your transport pipeline would be depending on how you group the sources of CO2, etc. And for those, we have developed a number of what we call high-level or low-fidelity models that basically would give a very good indication of the energy requirements would be and energy penalties on the power generation side, and then provide a good estimate on the OPEX side. We're also looking into extending that for the CAPEX, but obviously this is the whole intention of such a tool, is to be able to narrow down the limit on the CAPEX, and for that you need high-fidelity models. But at least for carrying out these high-level studies of basically how your OPEX would change depending on how you arrange your CO2 networks and so on, that certainly will work. And we expect that to contribute to government organizations and policymakers.
Okay. Okay. In the compression modules that you have, there's been quite a bit of work done in the US on the RamGen, which looks at supersonic compression technology. What modifications would you have to make to allow for those conventional compression technologies?
I have to say I'm not very familiar with the RamGen. I mean, I've heard about it, but I haven't done much background research on this. However, if this is something that can be described by certain performance maps, the compressor section models that we have in GCCS will allow you all different ways of specifying, whether it's 2D maps, 1D using affinity laws, or 1D dimensionless maps. this is all covered in there. So whatever you can describe with the map, that's something that you can integrate in there. Let's say the physics at a process modeling level is the same. Now, let's say for R&D people, engineers across the board who just want to have an idea of how the system would work, but do not have access to maps or don't have a vendor selected yet for the compression side of things, we've also incorporated let's say a mechanism that would allow you to use a reference map, something that applies more or less to, let's say, 70% of the rotating equipment that is out there. It will give you a reasonable level of accuracy in your simulations. So obviously, let's say, quantitatively it won't be exactly the same, but qualitatively it will give you a very good idea of where the system is.
Okay. Okay, I think we've got time for one more question. And I noticed that recently the University of Utah has announced that they'll be building a simulation of a 350 megawatt oxy-fired power station.
Yeah.
Have you heard of this approach, and is that similar or different to the approach that you're adopting?
Mm-hmm. Yeah, actually, this approach is focused around one single unit in the system, and that's the oxy-fuel boiler, if I understood it correctly from my research on and from my contacts with the University of Utah. So it will be a very high fidelity simulation of this unit operation in the system. Now, this is actually highly complementary to the work that we do here. In fact, our boiler model uses what we call performance curves that we have matched to a set of 9 different types of boilers, both supercritical and subcritical, that are out there. So we have data for these different boilers and match to those. If you have such a high detailed model, you could use this model to generate this performance curves and basically incorporate them in GCCS. That's what we call a third, if you want to call it, way of interfacing with GCCS. We call it model fitting or just model reduction. And you would be able to implement the results of such a high fidelity model in GCCS. An alternative way, and for that actually there's very good work from the University of Leeds in the UK. Professor Perkashanian was involved in there. I think it's a publication by Penny Edge, presented I think in the second oxy-fuel combustion conference in Australia, actually, that was back in 2011, that demonstrated how to couple a process modeling tool with a detailed CFD type model of a furnace. And basically, they carried out the model with the algorithms, CFD algorithms that or methods they had developed at the University of Leeds, and coupled these with a power plant model, process model in GPROMs. And I would envisage a very similar approach for the work that has been done in Utah, so that you could incorporate these results of a high predictive or high fidelity predictive simulation into a process simulation tool very easily.
Okay. Actually, one more question that's just come in, which is important. With a lot of CCS projects, a lot of people trying to determine how much does the project cost. Can you elaborate on the equipment costing package that's included in version 1?
Mm-hmm. Yeah. Version 1 will include a very basic costing capability. We've had lots of internal discussions, not only within the consortium, but also with ETI as to what they should contain. Because basically, let's say, some people felt that it would be sufficient for us to export an equipment list with the sizing information for that particular unit, so that costing routines externally would take over that work. What we've agreed on in the end is, for the first version, is to provide simple hooks so that people could connect their costing spreadsheets to the tool and basically run these sensitivity studies and calculations with their own costing. We have a prototype, though, that basically incorporates a calculation of annualized costs on the CapEx side, and on the OpEx side will allow you to look into different, let's say, loading scenarios for power plants, and would include different factors, installation cost factors, and so on, for the different elements across the chain. But this is something that we don't expect for the first release. It's something that will come a bit later, probably Q4 2014 or Q1 2015. But for now, we provide the hooks for external costing calculations.
Okay. Thank you, Alfredo. That's all the time we have for questions. If you have any further questions about Process Systems Enterprise or the package that was shown today, please direct them to Alfredo directly. If you'd like to provide feedback on this webinar or suggest topics for future webinars, please contact us at the Global CCS Institute. So I'd like to thank you all for your attendance, and a reminder that this webinar has been recorded and it will be available on our website in the next few days along with the slides. So I certainly hope that you found the webinar valuable, and once again, thank you to Alfredo for presenting. Goodbye and good night.